We will start after 5 minutes. Yeah, we'll start now. So, welcome to the week 9 live interactive session of NOC 24 EE-28 signals and systems. Course instructors are Professor Hitesh Shimali and Professor Kushal Gesha. And yeah, guidelines are as usual. Prerequisites include the last week's lectures that covered the following topics: the Fourier series of continuous time periodic signals and properties, and I'm sure you all would have gone through the lectures. Uh, and on top of that, I'm sure you all would have attempted the assignment 9 before watching the session. So let's go through a brief recap. So in LTI systems, the complex exponentials are eigenfunctions, right? What do I mean by that is, if I feed input e to the power s naught t, where this s naught is some complex number, this being a complex exponential, then this LTI system, the output of this LTI systems would be this h of s naught times e to the power s naught, right? So we can say that this e to the power s naught t is the eigenfunction, and this h of s naught is the eigenvalue, right? This would be a constant. So in a similar fashion, we can uh, comment on the discrete time counterpart. So we'll go through this continuous time case in detail, and then you can uh, one-on-one compare it with this discrete time analog. So this is our time convolution equation. Y of t is equals to minus infinity to plus infinity, h of tau x of t minus tau t tau. Time convolution. So now okay. Yeah. So y of t is equals to this e to the power s naught t is a constant in this integral because the variable of integration is tau. So e to the power s naught t will go out. We will be left with this minus infinity to plus infinity h of tau and this e to the power minus s naught tau beta. Right. Sorry, this should have been minus infinity. Correct. Now, what is this by definition? This is how we define the Laplace transform of a given signal, right? So y of t, we were able to express y of t as the product of e to the power s naught t, which was actually the input, and the Laplace of the impulse response and time domain. The Laplace of that is the S domain h of s naught. Okay, so what will happen is, say, for instance, I'll have some value of this s naught, right? Say e to the power. So I'll have, say, for example, s naught is 2j because it can be any complex number. Did not define any condition on this. E to the power 2jt, right? Suppose this is the input to the LDI system having impulse response h of s, right? The output would be the output would be h of 2g, right? The impulse response in S domain computed at s equal to 2g. That multiply by e to the power 2gt. Simple expression of y of t. Oh, this part is clear. Likewise, for discrete time case, our complex exponential, the form z power n, where z is a complex number, fit to a system having a impulse response h of z, then the output would be h of z times z of n. Again, the eigenfunction would be this, right? And this would be the eigenvalue computed at a particular value of z. Uh, so the proof for the continuous time case, this is for the discrete time case. Okay. So convolution sum can be written as y of n is equals to summation k varies from minus infinity h of k x of n minus k, well-known equation, and then we'll substitute x of n minus k by this z power n minus k. Right. Now in this summation, the summation is on the variable k, so we can take this z power n out. That is what I did. And then I'll be left with this summation k varies from minus infinity to plus infinity h of k z power minus k, right? And this is by definition the, should I say, the z transform, right? Z transform of h of k. That is a transform that is uh, that we'll see in the later lectures. That is defined for discrete time signals, and we'll probably see that in grade 12. Okay, hold on to that for a moment. So, what does this motivate us? Right, this motivates us to express our input as a linear combination of complex exponentials, right? Because if I do that, then since LTI system is linear, then what I can do, since LTI system is linear, I can mm, and evaluate the output as a linear combination of the individual outputs, right? For example, if I have input x of t, that is a1 e to the power s1 t plus a2 e to the power s2 t plus a3 e to the power s3 t, just an example in which our input was made up of three complex exponentials. The output would be simply the addition of these three, right? Where this a1 h1 h of s1 e to the power s1 t was the output corresponding to the first term, e2 h of s2 e to the power s2 t was the output corresponding to the second term, and similarly for the third term, right? So expressing the input as the linear combination of complex exponentials leads to a very convenient expression for the response of an LTI system. Okay. Yeah, similarly, our discrete time case will be handled. So now, although in general, the variables s and z, they may be arbitrary complex numbers, the Fourier analysis involves restricting our attention to some particular forms for these variables, and will focus on purely imaginary values of s. That is, our s would be j omega form, and thus we'll consider only the complex exponentials of the form e to the power j omega t, right? E to the power st, s in general is sigma plus j omega. We'll focus on this, so we'll have complex exponentials of the form e to the power j omega t, right? Now, determining Fourier series representation of a continuous time periodic signal. We know that a periodic signal can be represented by Fourier series like this, right, where this omega naught is the fundamental frequency and is equal to 2 pi by t, where t is the fundamental period, fundamental time period, and yeah, so the output would then be summation over k, ak. The output of this would be this, right? H of s naught e to the power s naught t. I utilize that result. So the fact that we are able to express the periodic signal by Fourier series, we can use that and write a simple expression of the output. Right? No need to compute that convolution anymore. So the task we are left with though is computing the Fourier series coefficient, right? AK. So in general, how do we obtain this Kn? An is equal to 1 over t integral 0 to t x of t e to the power minus j n omega naught t dt. I'm sure you would have gone through derivation in the lectures. So the point is we need to integrate over any interval of length time period t, right? It could be minus t by 2 to t by 2 or 0 to t, whatever is convenient. So remember this one, okay? Then continuous time Fourier series has some properties. Linearity is one that can be easily inferred. Then we have time shifting. What if the signal is time shifted? The Fourier series coefficients, they are multiplied by e to the power minus j k omega naught t naught, where t naught is the delay shift in the signal. Okay, and you notice that the magnitude of the Fourier series coefficient remain unaltered, right? Magnitude remains the same. The only change is the change in the frequency, right? This part is what is changing, phase and frequency. So then we have time reversal, which is actually a special case of time scaling. So if we have x of minus t, the time reversal, then the Fourier series coefficient would be a of minus k, right? So we'll just replace k by minus k in that case. In general, what if we scale by a general factor alpha? Then by definition, we would have this summation k varies from minus infinity to plus infinity ak e to the power jk alpha omega naught t, right? So this time scaling operation, it applies directly to each of these harmonic components of x of t, right? So um, Fourier coefficients for each of those components will remain same. And you can note that the Fourier coefficients have not changed. The Fourier, although these Fourier coefficients have not changed, but the Fourier series representation has changed because of the change in the fundamental frequency, right? Our fundamental frequency was scaled by alpha in this case. Then we have multiplication. Suppose we have two signals x of t and y of t having Fourier series coefficients ak and bk respectively, both having a time period t. Then if we uh, consider a signal that is product of the two x of t times y of t, the Fourier series coefficients are given by hk, right? And hk would be this expression, summation L equals minus infinity to plus infinity AL B K minus L. Okay, so we observe that this sum, right, of HK expression, right? This may be interpreted as the discrete time convolution of the sequence representing this Fourier series coefficients of x of t, and the sequence that represents the Fourier series coefficient of y of t. Okay, so a discrete time convolution of the individual Fourier series coefficients. That is what you can uh, remember to write this result. Then we have conjugation and conjugate symmetry. If we have a signal x of t with a time period t having a Fourier series coefficient ak, then if the conjugated signal is taken, right, x star of t, then what happens to Fourier series coefficient? The Fourier series coefficients are conjugated and time reversed, right? So taking a complex conjugate of the periodic signal x of t has the effect of the conjugation, the complex conjugation, and the time reversal on the corresponding Fourier series coefficients. You also would have seen this Parseval's relation for continuous time periodic signals, right? 1 over t modulus of x of t square, or integrated over the time period t, right? This is uh, the average power, right? The energy per unit time in one period of this signal, this periodic signal x of t. This is equal to summation k varies from minus infinity to plus infinity modulus of ak squared. This is the average power, right? So suppose for a particular iteration ak, this would be the average power in the kth harmonic component of x of t. So by the Parseval's relation, we understand that the total average power in the periodic signal would be equal to the sum of the average powers in all of its harmonic components. Yeah, that finishes the recap part. Can start with the questions. So the first one is the Fourier series representation is defined for what signals? Periodic, both periodic and aperiodic. The last option is neither periodic nor aperiodic. So this one is pretty straightforward, so we'll not waste time on this one. We know that Fourier series representation is defined for periodic signals. So go with option A. Second one, so for a periodic signal with the fundamental period t equal to 6, that is defined by this piecewise defined function, you need to find the Fourier series coefficient A0, right? And what is Fourier series coefficient A0 by definition? We saw just before that expression for A0 would be 1 over t integral over any time period t. I'll take 0 to t interval x of t dt, right? You can in fact think of it as area in the one period, right? Because the integral 0 to dx of t dt would be area in one period, all divided by t is our time period, right? This t. Let me shift this. Insert the page. So let's draw this signal example. One way would have been to compute it by definition mathematically. Right? Another way is to compute this A0 graphically. Since we know this integral 0 to tx of t dt would be area under the curve under one period. Right? Solving it graphically would be relatively simpler, so we'll proceed with that. From the definition is right from 0 to 2, it's t minus 2. This is 0. This is x of t. Okay. right? Why is that the case? Because this is -2, this is 3. When t is equals to 0, I'll be using this definition throughout this 0 to 22, right? When t is equals to 0, x of t would be -2, right? And when this t is equals to 2, this would be 0, so x of t would be 0. Since this is a linear function, I'll join the points by a linear line, right? Five, 6, okay. Now what about this interval, 2 to 3? 2 to 3, it is 0. It's 0 from 2 to 3. And 3 onwards till 6, the definition is t minus 3, right? When t is equals to 3, it is 0, right? When t is 3, this is 0, x of t is 0. And when t is 6, this would be 3. So 0 to 3 linearly varying from 3 to 6. 3 point is somewhere here. 3 is here. So join this, right? Yeah. Since this is periodic signal, it will repeat. See, it is a periodic signal with a fundamental period t equal to 6, right? From 0 to t, we have 6 units. So it will start repeating from there. So it would be again starting from -2. Sorry, it will start from -2 somewhere here and reach to 0 after 2 units, right? Likewise, on the left hand side, it will also repeat, right? So it should go to 0 in 3 units. This is -1, this is -2, this is -3. Right? So this is our signal x of t. And now what about this area in one period? So we'll take this 0 to 6 interval. Okay. In this interval, our area would be this area, right? Plus this area. We need to compute area of x of t under one period, and I'm choosing the time at time interval to be t equal to 0 to t equal to 6, right? So let's find this area. Area in one period 0 equal to 6. That is equal to These are two triangles. These are two, in fact, right triangles. So half of base to height, right? 2 times 2. This would be the area of first triangle. What about the second one? This would be half of base is 3 units. What about height? Height is 3 units as well. So this would be 2 times 2 is 4. 4 divided by 2 is 2. Plus half of 3 threes are 9. So 9 by 2. Right. So this is area, right? What about, let's do this. 4 plus 9 is 13. 1302. So this implies our A0 is this area divided by this time period. A0 will be equal to this area 1302 whole divided by time period. Time period is 6. It's mentioned in the question, right? So this A0 would be equal to 13 by 12. Which option is correct thing? This one. Then we move on to the third one. We need to determine the Fourier series coefficient AK, right? A general Fourier series coefficient AK for this train, this signal, right? Firstly, we need to see if this signal is periodic. If the signal f of t is periodic, which is the case, right? This is periodic with time period 4, right? Starts here and then it repeats. This point, this point, same. Similarly, this point, this point, and this point, same. So now that we know that this is a periodic signal of t, this could be expressed in terms of Fourier series representation. And in that representation, what is this Fourier series coefficient AK? We saw that this AK is would be equal to 1 over t integrate over period p. This interval could be any interval, any continuous interval, provided the length of that interval is equal to the time period. Right. You could use 0 to t, you could use minus t by 2 to t by 2, whatever you need. And f of t e to the power minus j k omega naught t dt. Right? So ak would be equal to what would our ak be equal to? This t is 4, right? So this would be 1 over 4. Let me take the interval to be minus t by 2 to t by 2. Okay. So I'll take the interval to be. You have the flexibility, you can proceed with any interval and verify you'll get the same answer. Okay, so t is 4. Sorry, this is minus t by 2 to t. T is 4, so this would be minus 2 to 2, right? This interval. In this interval, this is signal that falls under this interval. I mean, in this interval. So we evaluate minus 2 to 2 under this. What is okay? This is f of t e to the power minus j k omega t dt. Right. So we need a page. And now I know that this EQ is equal to this. But in this interval minus 2 to 2, it is 0 from minus 2 to minus 1, and it's also 0 from 1 to 2, right? This in this interval, f of t is 0. So I will change the limits of my integral from minus 1 to 1. Because from minus 2 to minus 1, it is 0. Likewise, for 1 to 2, it is 0. So 1 by 4 integral minus 1 plus 1, because the signal is non-zero only for this interval. And in this interval, the signal is 1, right? Unity. E to the power minus jk omega naught t dt. So yeah, ak would be equal to 1 over 4. We'll integrate this e to the power minus jk omega naught t. We'll be left with e to the power minus jk omega naught t whole divided by minus jk omega naught. Right. The limits are from t equal to minus 1 to t equal to plus 1. So our EQ would be equal to 1 over 4. And I'll use this upper limit, t equal to plus 1. I'll get e to the power minus jk omega naught. Right? Wait. When I use this, I'll get e to the power minus jk omega naught plus e to the power plus jk omega naught. So then we'll left with some manipulation 1 or 4. And we take this k omega naught common. out is minus j can be written as 1 over j, right? So I will do both simultaneously. 1 over j will make j go to the numerator. This k omega naught would be here, right? And then I have e to the power minus jk omega naught minus e to the power jk omega naught. What is your omega naught? Your omega naught is 2 pi by t. That is your t is 4, right? When t is 4, this 2 pi by t would be pi by 2. That's t is 4. So I'll use that. Ak would be equal to uh, this would be j 2k pi, right? This 2 cancels. I mean, 4 divided by 2 is 2. That's what I did. Also, inside the braces will have minus jk pi by 2 minus e to the power jk pi by 2. I'll absorb this minus sign. See, I'll take this minus out, right? This would be minus j. Then I'll write minus j as 1 by j. I'll bring that j in the denominator. I'll bring 2 also in the inside the braces, right? So I'll be left with following 1 over k pi or pi k. Since I had taken this minus sign out, this would be e to the power jk pi by 2 minus e to the power minus jk pi by 2, right? And in the denominator, I'll have 2j. This 2 is this, and this is the minus j. It has 1 by j, since I had taken minus sign. Now it's straightforward. AK would be 1 over pi k. This is sine of k pi by 2. Right? So that is how you solve such questions. So option B was correct. Stacy. Right? We are done with the third one. We move on to the fourth one. So for this figure 2, we need to determine the frequency domain representation y of j omega of this y of t. Firstly, what is this y of t? This y of t is the sum of the two signals x1 of t and x2 of t. We are given that x1 of t is x1 of t plus x2 of t, right? So we can write this y of t as a sine of omega 1t plus a sine of omega 2t. Okay, then I'll express this sign in terms of complex exponentials. After taking this a common, I'll have y of t is equals to a, the sine of omega 1t can be written as e to the power j omega 1t minus e to the power minus j omega 1t whole by 2j. In fact, I'll take this here, otherwise I won't be able to write it in a single line. And then I have plus this one. So I have e to the power j omega 2t minus e to the power minus j omega 2t whole divided by 2j. Right? Now I need to take the Fourier transform of this. So what would be our y of j omega or y of omega? Right, before that, tell me one thing. What is the Fourier transform of 1? Fourier transform of 1 is 2 pi del of omega. Very simple result. So I hope you all remember the frequency shifting property of Fourier transform, right? If I shift so omega naught, what will happen to the time domain signal? It will be multiplied by e to the power this exponential, right? J omega naught. Okay, so we'll use this one as we have done earlier as well. So for all these complex exponentials, we'll in Fourier transform, we'll find them in terms of their delta function representations. Let's do that. I of y of j omega will be equal to a by 2j is constant factor. I'm taking that out. All right. I'll be left with this minus this. In fact, I can take this. No, those two steps. So this e to the power j omega 1t. The Fourier transform of that is 2 pi del of omega minus omega 1 minus 2 pi del of omega plus omega 1, right? Because we have minus omega 1. So minus omega naught is plus omega naught. Likewise, we'll have 2 pi del of omega minus omega 2 minus 2 pi del of omega plus omega. Right now, I'll take this 2 pi common and rearrange y of j omega would be a uh, 2 pi is 2j del of uh, omega means omega 1. In fact, this is del of omega plus omega 1 plus del of omega minus omega 2 minus del of omega plus omega 2. Right? This j can be like this 2 and 2 cancel out, right? Will I be left with y of j omega, and that would be equal to j. I'll take into the numerator, writing it as minus j minus j by a, right? And then I'll have this a and paste it. Saves the time. Y j omega would be, I'll multiply, I'll multiply this whole term by this negative sign. This negative sign. I'll be left with j by a multiplied by signs will change. This would be negative, this would be negative. So I'll have del of omega plus omega minus del of omega minus omega 1 plus this one, right? Del of omega plus omega 2 minus del of omega minus omega 2. Mistake. Rest is fine. So I'm comparing with the options. Our option A is correct, right? That finishes this fourth question. Our fifth question is, if A is the Fourier series coefficient of the periodic signal x of t with the time period as t, then the Fourier series coefficient of x of t minus 2 is. This is in fact given readily by the properties of Fourier series coefficients, which we already saw. So I'll directly write the result. Given x of t has Fourier series coefficient ak and Fourier series coefficient ak, and this is periodic. With period t, then the time shifted signal x of t minus 2 will have Fourier series coefficient of same magnitude, right? But uh, it would be an exponential factor multiplied, complex exponential factor multiplied. So we'll have ak exponential of minus jk omega naught 2, right? Because it was shifted by 2. What is this omega naught? This omega naught would be 2 pi by t. Right? It's right. It doesn't. Omega naught would be 2 pi by t. So this would be ak exponential of minus j a. Omega naught is 2 pi by t times 2. So therefore, x of t minus 2 Fourier series coefficient of x of t minus 2 would be this ak would be this ak times this exponential minus jk. 2 and 2 are 4, right? Minus 4 jk pi by p. This would be your answer. So option A is correct. We'll move on to the next sixth question. For the periodic signal x of t, x star of t, the complex conjugate, and the time reverse signal x of minus t. Note that we are using two operations on x of t here. What would be the Fourier series coefficient? Okay, this will have a Fourier series coefficient bk, and you will need to determine p5, right? So bk at k equal to 5. That is what you need to determine. But you need to determine it in terms of this AKs, right? So you need to find a relation that will hold good. See, this is something that is given that x of minus t. I mean, this is something that is known, but Fourier series coefficient of x of minus t would be a minus k, where ak is the Fourier series coefficient of x of t. Okay. If we time reverse the Fourier series coefficients, I mean, we need to replace their k indices by minus k. Now, what about the complex conjugated signal of x of minus t? X star of minus t. Fourier series coefficients would be when we complex conjugate the periodic time signal, continuous time periodic signal, then in the Fourier, their Fourier series coefficients, they are complex conjugated and they are time reverse, both operations. So this is our first operation. Using a different color would help. Yeah. So firstly, I'll take this one, minus. Okay, this is a A. Due to complex conjugation, uh, firstly, my Fourier series coefficients are complex conjugated and they are time reversed as well. So minus of this minus K, that is equal to A star of K, right? So my BK would be A star of K, complex conjugated Fourier series coefficients of AK. So in particular, what about B5? Would be A star 5, right? Here the star is the complex conjugation. Which option is correct? The first one, right? Fine. Let's move on to the next one. In question number 7, you have, yeah, for question number 7, you have two arbitrary signals, x of t and y of t. They both are periodic and they have time periods t1 and t2. Uh, their Fourier series coefficients, uh, they, they have Fourier series coefficients ak and bk respectively. So what would be the Fourier series coefficient of 3 times x of t plus 4 times y of t? Is a good question. So how would you proceed on this one? We use the linearity property of Fourier series coefficients, right? Since AK are the Fourier series coefficients of x of t and BK are the Fourier series coefficients of y of t. So we'll do for you know x of t, y of t series coefficients, right? So 3 times x of t would have Fourier series coefficients 3ak, and 4 times y of t would have Fourier series coefficients 4bk, right? I've used the homogeneity of Fourier series coefficients up to this point. Now I'll use the superposition. So I can write 3 times x of t plus 4 times y of t. The Fourier series coefficient of this resulting signal would be the superposition of 3ak and 4bk. So 3ak plus 4bk. Simple. Option B is correct. Now, um, yeah, given that this x of t is real and periodic signal with the Fourier series coefficient as ak, okay, if a2 is equal to 3 plus 2j, what will be a minus 2? Okay, x of t is real and a periodic signal, and it has a Fourier series coefficient ak. If a2 is equals to 3 plus 2j, we need to determine a minus 2. So we'll proceed for this one as follows. If this is something that was given, x of t Right. If A2 is equals to 3 plus 2j, right, it is given. We need to determine A minus 2. For such questions, you'll proceed as follows. Make sure you try this one out before proceeding with the solution. I mean, before seeing the solution. So we know that for a periodic signal, x of t, right, complex conjugated signal star of t, the Fourier series coefficients for that are given by this a star minus q, right? We saw this result multiple times in this session today. So now what is given is that this signal is real, right? I'll write it. Since x of t is real, if it's real, then this x star of t will be x of t, right? Because for a real signal, taking complex conjugate of a real signal would give us back original signal because it's real. Imaginary part is a. So now, what do we conclude from this? We conclude from this that this a star minus k will be equal to ak, right? So what about a minus k, right? Now you have ak equal to a star of minus k. If what about a minus k? If I replace k by minus k would be k, right? So now we are interested in obtaining what is a minus 2, right? We know a2 was 3 plus 2j. A2 was 3 plus 2j. Right? That is complex conjugate of A2. That will be 3 minus 2j. Right. So A minus 2 would be equal to this A2 star. Right. And that is 3 minus 2j. So from such questions, we will proceed like this. So which option is correct? Option B is correct. So yeah, this table summarizes the properties of the continuous time series. You can refer to the book for this table. I've used snap from this book that is recommended for this course as well by the instructors. Let's briefly go over them. This is something that we saw. Time shifting. We also saw this. Frequency shifting, conjugation, Fourier series coefficients are conjugated and time reversed. X of minus t, a minus k. Time scaling leaves Fourier series coefficients unchanged, though Fourier series representation is changed. We have more properties. What if we have periodic convolution? In that case, Fourier series coefficients are written as this. Multiplication is something that we saw. I discussed it. What if we differentiate a signal? Important one, right? If we are given a signal whose Fourier series coefficients are AK, if we differentiate the signal in the time domain, then the Fourier series coefficients are given by this, right? JK omega naught AK. Likewise, you can compute the Fourier series coefficient for higher order derivatives, right? d2x of t by dt square and so on. Then we have integration. If the signal is integrated from minus infinity to t, assuming it's finite valued and it's periodic, only if a naught is 0, then you can have this one. Okay, the Fourier series coefficient expression is this one. This jk omega naught is divided in, while differentiating, this jk omega naught was getting multiplied, and it would be multiplied for subsequent higher order derivatives as well. So for objective type questions, this is handy. Have an eye on them. Uh, Conjugate symmetry for real signals. If x of t is real, then we have following properties that hold good. This is something that we saw in the previous question as well, right? AK is equals to a star of minus k if x of t is real. But in addition to that, we have following. The real part of AK is the real part of a minus k. I hope this is intuitive, right? Why? Because see, real part of AK, that would be real part of a star of minus k, right? And real part of a complex conjugated signal is the real part of the signal that is not conjugated, right? Simple. So what do we conclude? That this real part of AK is equals to real part of A minus K. Right, I'll remove annotations. Likewise, what about this one? Imaginary part of AK is equals to minus times imaginary part of minus AK. Again, we'll proceed similarly. Imaginary part of AK, keep this in mind, can use all of these results when given signal is first of all periodic, only then it will have Fourier series coefficients. In addition to that, we have a condition that the signal should be real value. You'll encounter many such signals, right? And for all those signals, you can use these properties. So imaginary part of AK is equals to imaginary part of this A star of minus k, right? I use this one. For this one, we saw proof already, right? I'm trying to prove this one right now. So this is imaginary part of AK. That's equal to, okay, now suppose a signal is complex conjugated, right? Signal is complex conjugated, right? It's imaginary part. What? Okay. Suppose I have this one. Imaginary part of A, imaginary part of A star. A3, that imaginary part of any general signal A would be minus times the imaginary part of A star, right? This is intuitive. So likewise, imaginary part of A star would be equal to minus times imaginary part of A, right? So I can write imaginary part of A minus K, but with a negative sign. So that is how this property comes about. Similarly, mod of AK is equal to mod of minus A. I'll show you this as well, and then you will try out other yourself. So see, AK is equals to A star minus A. Okay. Modulus of AK. What would be that? Would be modulus of A star of minus K. Right? Simple, taking modulus on both sides. But this is equal to modulus of A minus K. Why? Because if you have a complex number Z and its conjugate Z star, their modulus are equal, right? Because modulus by definition is square root of real part of Z, imaginary part of Z, but both are squared, right? Although imaginary parts are negative, I mean, imaginary part of if imaginary part of Z is positive, its imaginary part would be negative. But anyway, since imaginary part is squared, so they both are equal, right? So that is why modulus remains same. I'm sure you already know this, but still thought I would revise this. So that's how this comes about, right? You can try this one yourself. So now think of this as follows. You will be given any question we saw previously. The question was given on this pocket, right? But a question can be asked from any of these properties, right? So keep the picture clear in your mind. So what if we have real and an even signal? In that case, the AK is real and even as well. Okay, what do we mean by even AK? Right, real we understand, right? What about even AK? Even AK means that AK is equals to A minus, sorry, A minus K would be equal to AK. Odd AK would be A minus K is equal to minus times AK. Simple, right? What about this real and odd? If we have x of t as real and our x of t is odd as well, then it turns out AK is purely imaginary and odd, right? I'll suggest you to try both these, come to conclusion that they make sense. If not, you can drop me an email and then we can discuss. So now, yeah, this is even odd decomposition of the real signals. If x of t is real and suppose we take its even part, then Fourier series coefficient, although wait, you need to take the real part of that AK, where AK is the Fourier series coefficient of x of t. Right? This one is readily from this one, right? Likewise, this is readily from this one. I mean, Parseval's relation, we saw this as well. You could have been asked a question from this as well. So, in short, this table summarizes this session in one page. Okay, so we'll end this here since there is no one here to ask any questions. So, if you have any questions, you can let me know in the comments or you can drop me. Okay. So I'm signing off. Bye.